Hello, and thank you so much for watching this presentation. My name is Himan Abdullah Puri from University of Colorado Boulder. I'm a PhD candidate, and this is a joint work with my friend Masood Mansouri from Eindhoven University of Technology. Our work is multi-sided exposure bias in recommendation. And I would like to start the presentation with a question. Did you know that the richest 10% of adults in the world own 85% of global wealth, while the bottom half collectively owns barely 1%. So now you might wonder why all of a sudden I'm talking about economic and wealth in a recommendation system workshop, but we do have a similar problem in recommendation systems, and we call it popularity bias. For instance, in music, we have super popular artists like Drake, and then we have some non-popular that not everybody might know about them. For example, Kehan Kalhor, who is a Persian musician. Okay, so if I want to explain the popularity bias in recommendation, I want to show you this plot. So this shows a typical distribution of popularity for different items in a given recommendation systems. So on the horizontal axis, we have the items that are ranked from the most popular to the least popular, from the left to the right, and then on the vertical axis, we have the popularity of those items. So for instance, we can see so we call this actually a long tail distribution, yes. So we can see actually three different item categories. So on the far left, we have few popular items. We call them head or H items, that they are super popular, okay? In the middle, we have some more items, so that's definitely more items than the H items, but they are not as popular as the H items. And then finally, we have a lot of tail items, like non-popular items, that they are not getting as much attention as the rest. So for example, Drake will be on the far left of this plot, and then Kehan Kalhor will probably be on the far right side. So we are interested in measuring algorithmic popularity bias, how algorithms might propagate this bias. So for the experimentations, we have used two publicly available data sets, one from the music, one from the movies. So Last.fm music, Movie Lens from the movies. You can see the information for each data set here. So for Last.fm, we considered albums as the items and artists as the suppliers. For the Movie Lens, well, movies are the items and the directors of those movies are the suppliers. And we have used 80% for the training and 20% for the test. And for each user, we recommended a list of 10 recommendations. We are going to only show Last.fm here in the presentation, but the full result can be seen on the paper. Okay, so for the algorithms, we have picked several different algorithms from different classes of recommendation systems. So from the neighborhood models, we have used two algorithms, so user-based collaborative filtering and item-based collaborative filtering. And from the latent factor models, we have used bias matrix factorization. And then we also included a very simple baseline just to show the extreme case of popularity bias, which is called a most popular algorithm, and it recommends the most popular items to every user as long as they have not rated those items. So here we see an interesting information here. So this shows the cumulative frequency of different items in the rating data and in the recommendations for different algorithms. Okay, so we can, let's say, focus on the biased MF here, for example. So we still see these three item categories on the top of each plot, H, M, and T. So we see that items that belong to H category in the rating data, they take 20% collectively together, right? Okay, so now in the recommendations, they take how much? 80%. So that's an amplification of around 0.6, which is actually 4 times amplification. On the other side, so items that belong to H and M, collectively, these items from these two categories, collectively 80% in the rating data of the interactions, but these two, they take almost every recommendation. So basically, there is nothing left for the tail items, right? Okay, so is popularity bias only affecting the items? Is it only an item level problem? Well, we need to look at the recommendations in a more a closer way. So historically, we see recommendation system like this. So we have some users, we have a recommender system. we give recommendations to these users and they give us feedback. And I've shown every user with the same color just to emphasize that that's how we see users, like in general, before we have this multi-stakeholder view recently, that we say actually users could belong to different groups based on gender or based on their interest, country, anything. So that's each group of user could be stakeholders, and also users in general could be stakeholders. And we have also the suppliers of these items, right? So the people who provide and supply those items are stakeholders. And there might be some other side stakeholders as well, that they might impose some constraints and limitations. And for example, the society and even law, or even within the company, there might be some side stakeholder that they might have, for example, needs and preferences. We only focus on the main ones here, the users and the suppliers. So, okay, so now we have users and the suppliers. We want to measure the impact of popularity bias on each of these, on users and on the suppliers. So we are going to first focus on the users. So we need to see this. So users, first of all, are not equally interested in popular items, and that's the fact, right? So in this plot, we show we show the ratio of 3 different item categories: H, M, and T, popular, almost popular, non-popular items for every user in the last FM datasets. Well, users are sorted from the highest interest towards the popular items, to the head items, to the least interest. So from the left to the right. And we created like 3 different groups of users for a better comparison of different users. So we have G1 are those users with the highest interest in popular content, G2 somehow interested, G3 with the least interest in popular content. So for example, in G1, we can see the red color, which is the non-popular items, are in the bottom, versus for the G3, we can actually see the blue is in the bottom, which are the popular ones, which means G3 are not as interested in popular items as G1. Okay. So that's what we saw for the rating data, okay? And now let's see how the recommendations look like for different users in terms of these 3 item categories. And that's how it looks like for different algorithms. So in the rating data, again, we saw a lot of red, which were the tail items for different users. Even for those on the left side, we still have red, like somehow maybe 20% of their profile could be red. But let's say the user CF and item CF, basically no red, no tail, no non-popular item is being recommended, okay? And for bias MF, we see for some users, some red is being recommended, but definitely not as the other one. And then also the blue is much more in all these algorithms, much more higher percentage on the top of these plots. And most popular, obviously, well, no red and no meat is being recommended, which is what we expected, okay? So now, okay, so it does impact users, every users. It impacts some users more because they had less interest in popular item, but they still get a lot of popular items. How can we measure that? Well, we propose this user popularity propensity deviation, UPD, which uses 2 different ratios for the calculation. So first, we need the user's propensity towards different item popularity groups. We show this by C giving U, so C is an item category. And then we have the same ratio for the recommendations, so the ratio of item popularity groups in the recommendations. Once we have these 2 for every item category, we have 2 different distributions, capital P and capital Q, P for the profile, Q for the recommendations. We can use some statistical distance measures. We have used, for example, here Jensen-Shannon divergence to find the distance between 2 these distributions. And once we have that, we can actually measure UPD by taking the average of this distance between different users and then between the different groups of users, and then we can have the final UPD. Yes, so that was for the users, okay? And now we can see also how it impacts the suppliers, right? So suppliers also have, some of them are more popular, some of them are less popular. We need to see how the recommendations impact different suppliers. Okay, so here we have a similar information that we had for the items, but now it's for the suppliers, okay? So here on the top of each plot, we have shown 3 supplier groups based on the popularity. So S1, super popular supplier. So here we talk about Last.fm, which means artists. So super popular artists. S2, kind of popular artists. S3, very non-popular artists. So for instance, here we can see that suppliers or artists that belong to group S1, the popular ones, they take up 20% of the rating interactions in the rating data, but they get 40% of exposure in the recommendations. So that's an amplification there, right there. And then the one that are kind of non-popular, they still have some exposure in the rating data, right? So we can see that here, that they have some exposure, but in the recommendations, actually, items that are from the non-popular one, they don't get any exposure. Why? Because actually items from S1 and S2, they already take up around almost 100% of the exposure. So there is nothing left for S1. So basically zero exposure. Okay, now we want to also measure this. So supplier popularity deviation, SPD. We need, again, two different ratios. One, the exposure of supplier group S in the rating data, how often items from that supplier group is being rated, and the same exposure in the recommendations, right? How often it's being recommended. And we can have a distance between these two, and that will give us, so on average, this will give us the SPD, or supplier popularity deviation. So the takeaways here. So popularity bias impacts different sides of a recommender system, right? We saw that it impacts the users, it impacts the suppliers, and we need to make sure that we are measuring all of these correctly. Okay, and algorithms, we also saw that they propagate this bias, right? So some of them, they intensify, some of them, they intensify more than the others, and that's also important to make sure that we know. And then in this work, we proposed some metrics to measure how much exposure bias we have for different algorithms, for different sides or stakeholders of the recommendations. And with that, I finish my presentation. Thank you so much for watching this presentation. You can see the QR code of the paper here, and that's my Twitter handle. And also, well, since we are researchers in the recommendation system community, maybe sometime we could give each other a human-to-human recommendation. So I would like to give you Taste of Cherry by Abbas Kiarostami and Tokyo Story by Yasujiro Ozu, which are two great movies that I would recommend you to watch. And again, thank you so much for watching this presentation, and hopefully we can stay in touch. Thank you, and have a good